Okay, ladies and gentlemen, thank you for your participation in this session. The session category is the automation and robotics, and we have 5 different papers from all over the world. The first one will be presented from the researchers from the Poland and India. The second presentation will be done by researchers from Turkey. The third one by a researcher from the Lithuania. The fourth one from the Poland, and finally the fifth one is from the Slovenia. Also, I should say that every presenter have totally 15 minutes to present and 3 minutes for the conversation around the walk. Furthermore, if I want to introduce myself, I should say that my name is Davood Ghaderi, and I am a faculty member in the Bursa Technical University at the Department of Electrical and Electronics Engineering. So, for the first presentation, I would like to invite to Mr. Pawel Dworak from the Poland to present their study entitled Effective Use of MPC for Dynamic Decoupling of MIMO Systems. Scene is yours.
Mr. Chairman, gentlemen, on behalf of myself and my friends from India, I would like to present results of our research on our research how to solve the problem of dynamic decoupling, which means what is. I will start from what is a dynamic decoupling. It is a problem connected, which is connected with dynamical system with many inputs and many outputs, and it's obvious that in general all inputs influence all outputs, and the task is to again in general to construct a system to be able to change the value of only for instance only one output separately from any others, and there is it's a not new problem. It was analyzed from decades, but in general many dynamic decoupling methods treats with linear plans, and many of them are constructed for square ones, which it means that for objects with the same number of inputs and outputs. Okay, today I will show the simple example and experiments with also linear and a square plant. Very simple because of the plant which has 2 inputs and 2 outputs only, but it was chosen just to show clearly the results. But what is the main problem in such such control systems is that a part of course dynamic decoupling, we have to also ensure of course stability, dynamic in each separated loop, control loop, and of course which is very important is there are some constraints, input constraints, for instance. In case we are not able to satisfy these constraints in case of such complicated control loops, we may seriously deteriorate effectiveness of control and even lose stability. That's why we are trying to find a method how to compare to the classical approach decoupling, how to use model predictive control algorithm and this idea to to both, of course, control the plant and to solve the problems with dynamic decoupling. And it is possible, of course, and I say in a few minutes how to do that. In general, as I said, we're trying to analyze the possible ways of using predictive controllers to perform all control tasks. First of all, the decoupling, and we try to make some recommendations how to use properly such controllers. Here we see a typical control scheme of as I said before, 2 inputs and 2 outputs planned. Linear one, just for simplicity, but what it is for, just to present that a typical situation is to treat as such plant and construct a distributed control system and treat each, let's say, path separately, disregarding all these crossings. So typically we have 2 different controllers for 2 control loops, and these crossings, these interactions are neglected, or of course that they are treated as some disturbances. In case of theta, of course, as I said, there is a lot of different proposals how to construct dynamic decoupling systems. In case of theta systems, we were able to construct a dynamic decoupler here for in a scheme called inverted decoupling. It is very simple. We have very simple formulas how to ideally decouple the system. And again, with this dynamic decoupler, we have 2 separate two controllers and 2 separate loops, control loops. But of course, not all plants are such simple, and in general, we have much more. We can have more inputs and more outputs. The number of inputs and outputs are maybe different. And such simple schemes and such simple ideas as distributed control system with separate controllers are not proper, and will doesn't solve the problem. That's why we try to use a model predictive controller in which in general we try to minimize the criterion. Typically such criterion consists of has 2 parts. First related to the control error, second to the control signals. We try to minimize this criterion. And of course, why we can use model predictive control to solve the task? Because for each of these parts we have some additional matrices, weighting matrices, which we can use, in one way. To modify this criterion during the operation, and of course we can minimize this criterion, taking into consideration some other constraints. And I will show you, because we have to solve this equation, solve this criterion. Subject to some hard constraints composed on control signals and also outputs, and that's the 2 main ways how to use this MPC controller to solve the task. I mentioned that we can also, but in general, in any type of control, we can shape the reference signals, and it's a typical way in model predictive control also. But as I said, because we can do that in any control scheme, we don't treat that as a proper and some specific method. The first method we treat as a decoupling one is to adjust weighting factors in, as I said, in these weighting matrices. Typically, they are used as an identity matrix or even zero matrix, or some diagonal matrix with some coefficient lambda, which are taken somewhat when we tune this model predictive controller. But in fact, we can modify that, and we can introduce some specific coefficients for each control output, the error, or for each control input, because we have these two matrices which are diagonal and constructed with these coefficients. The same is with we can solve this criterion with adjusting output constraints. So we can specify minimal and maximal values of outputs, which should be calculated and should be obtained during the regulation. And it is also possible, of course, not maybe ideal decoupling, but we can assume that there is, for instance, plus minus 2% from the reference value, and specifying that we are able to solve, to minimize this mutual influence of the inputs and outputs. In the paper, we present some tables and results of simulations for a reference model, for a reference plant taken for a wood and berry distillation column, which is very often used as a reference one in any works connected to dynamic decoupling, and we can compare six different PID type controllers with different model predictive controllers tuned by using changing weights and output constraints for different prediction and control horizons, just to check which construction, how to tune properly, and which situation is the best. Of course, it's not time for analyzing that. It's taken from the paper, but as we see here, we present the results of PID controllers obtained by using a PID controllers, and if we compare that with those results obtained by from MPC one, we see that MPC outperforms PID in each time. So we see that the mutual influence is considerably reduced, and we can use so the control objective is to minimize criterion like 2. Okay, we don't guarantee a perfect decoupling, but we can considerably reduce the input-output interactions, and because the criterion is calculated at each sampling time, so we can modify that the outputs constraint, and it may be easily implemented in everyday practice. And these MPC controllers may be also used for it may be also easily used to control nonlinear plans, for which, in fact, we don't have any universal decoupling method. Thank you very much for your attention.
So, is there any question to ask? Please.
This distillation column that used the model of distillation column.
Mm-hmm.
What are the input parameters and what are the output parameters?
To be honest, I don't remember exactly because for us in this paper we use this as a reference one. Is just a simple theoretical model. Yeah? But if I could remember, there is a concentration of some inputs, and there is also a temperature or something like that.
Okay, thank you. And another question? Yes, please.
Why you decided to solve this problem? It is related to some project or some concrete object or just?
In general, it's I'm considering the dynamic decoupling as a problem from many years, and so it's yeah. I'm interested in that in control of objects with many inputs and many outputs, and to solve such problems. Yeah.
Okay. Any other question? So I ask the final question. In your example in equation 7, can you show again? Yes, yeah. For this example, we can see these terms that show us the delays, yes, in the system. Okay, how can your proposed method can control the structure by consideration the interference signals and noises with consideration of this delay values, parameters?
If I see here, okay, we don't see that exactly here.
Mm-hmm.
Of course, we have to, in classical methods, we have to know the model precisely.
Mm-hmm.
For model predictive controller, we also should know the model as best as possible.
Yeah.
I didn't mention that this plant for model predictive control has been discretized with and this discretization also took into account this delay. It was a discretization with the step 1 second.
Mm-hmm.
So if we know this even continuous model, we can construct a discrete one, also which has in its structure this delay. And in this model predictive control, of course, we should consider controllers with prediction and control horizon, at least prediction horizon, which is longer than the delay we have.
Yes. Yeah? Okay. Thank you. Is not any question. I want to thank you again for the good presentation. And I want to invite to Mr. Akif Durdu from Turkey to present his study entitled Sliding Mode Controller for Position Tracking of a Servo System with a Variable Loaded DC Motor.
Hi, I am Akif Durdu from Turkey, Konya Technical University. I'm an assistant professor. Sliding mode control for position tracking of servo system with a variable loaded DC motor. First of all, I will introduce my presentation, and after that I will give some information about sliding mode control theory. And after that, we quasi-rotary servo system that we use in our application. And after that, I will give experimental results and our performance criteria, and after that I will give testing results and this discussion, and I will conclude my presentation. The real-time position control of servo system is carried out using sliding mode control method. DC motors are commonly used in many industrial applications and robotics. Studies in this paper have been tested in DC servo system, which is designed and produced by Quanser. 3 different types of sliding mode controls are designed for position control of servo system, and later performance comparison of DC motor on servo system are made in this study. It's shown that CMC method is robust against disturbing effects, variabilities and uncertainties on the system. Outstanding part of this paper is that designed controllers are implemented in real time to servo system with a variable loaded DC motor. It's shown by means of this study that this control structure can be performed as high performance in the real-time motor control applications. DC motors are widely used in angular position control applications, which are often encountered in industry. They have been certain characteristics such as high efficiency, successful performance, and easy controllability, and thus they are widely preferred in raw steel mills, electric winches, and robotic manipulators, and many industrial applications. Precise position control constitutes a requirement in many servo applications, such as positioning of a robot arm from space research to medical field. In position control, motor speeds and position information, as well as performance of controller, accuracy of controller, and response time of the system are important. In many industrial applications where PID controllers are widely used, position control has created a major problem for many years. Although PID controllers can be designed easily, they have several disadvantages about robustness against system uncertainties and external disturbing effects. They cannot produce successful results in nonlinear control applications. Even if a good performance characteristic can be obtained by classical PID parameters, when operating conditions change and expected performance cannot be achieved by using PID controller with fixed parameters. DC servo motor control systems have usually uncertain and nonlinear characteristics which affect negatively to controller. Therefore, it is needed a self-adjusting adaptive control or a robust control given rapid response. Sliding mode control theory. The theory of CMC is based on variable structured control technique. CMC, which shows insensibility to systems parametric changes and distributing effects and can operate under uncertain conditions, is a robust control method for linear and nonlinear systems. Thanks to these advantages properties, CMC draws much interest in machine control applications. Conventional CMC theory is composed of 2 phases, which are reaching mode and sliding mode, as can be seen in Figure 1. The most important design step is to create a sliding surface. High frequency switching control signal in Figure 2 moves states of the system or significant surface. Movement on surface is described as sliding mode, and also movement up till reaching the surface represents reaching mode. The main purpose of the CMC is that system output arrive to desired output the desired system output. The control signal UT that tracking error converts to 0 and keeps to minimal level is produced. The first step to design the CMC is to sliding surface. The control law UT that its purpose of the CMC consists of the two parts as equivalent control signal UAQ and switching control signal USW. Key is a positive number which is selected a quite big suppresses system uncertainties and unexpected dynamics and signum function. Signal USV pulls states of the sliding surface while S2 not equal to 0 after reaching the sliding surface, so switching control is switching off. Equivalent control is a continuous. Switching control signals is discontinuous. Lyapunov function is shown this equivalent Lyapunov function is commonly used for sliding mode, and system stability law is obtained by this equations. Convergence condition is described in 7 this, and sliding condition is defined in equation 8. System arrives sliding mode if condition ensured. Conventional CMC has advantages such as robustness. It has disadvantage which is known as chattering phenomenon. Chattering phenomenon emerge from high frequency switchings and sharpness in this signal function, even if its effect may not be seen much in simulation studies when real-time applications are carried out. It is understood that chattering phenomenon is a significant issue that needed to be considered. It may causes breakdown and adverse effect, audible sounds, and heating of the power circuit in the controlled mechanical system. Quasi-rotary system. We use this quasi-rotary system in our application. This is a block diagram of this mechanical system, and we put load this system there, and we use MATLAB program for this application with this block diagram. And also this quasar mechanism has these parameters. We use these parameters on the MATLAB program in the Simulink, and this transfer function and mathematical modeling of the quasar system. This system has this mathematical model, and also we use these parameters in our system. In this study, analyses are made by added to motor in different levels by means of addition loads. Firstly, initial loads, and later for loading low and high weighted metallic objects. 3 types and loading condition are performed and results and analysis. Servo system can be modeled approximately as a first order system to actualize the speed control. Additionally, degree of the system for position control is shown second order. Transfer function of the servo system and for angular velocity and angular position are described in below. This is transfer function, angular velocity to linear velocity. Key and T. Key. if transfer function of the system converts the state space model, it is obtained as like this. This is state space representation of the system. First of all, we trained the conventional CMC method. For this method, the mathematical model is given like that. This part is given our paper, and also modified CMC. This modified CMC method, a modification in the signum function is done and replaced a smooth transition nonlinear sigmoid function. The modification is that. After that, PID control are prevalently used in many different specific files like robotics, unmanned aerial vehicles, chemical industry, stamp production, oil processing, and motor control and automation systems. And also we add the PID. We use CMC with PID control, and I will show the results at the results section. And performance criteria in the control system specific some performance criteria which are generally used to measure and compare system performance are available. In this study, evaluation are carried out for different criteria: integral square error, integral absolute error, and integral time-weighted absolute error. Therefore, calculation formulas of these criteria are shown here. Testing steps and discussion. By determining a sinusoidal reference for position tracking, response of the motor system is analyzed according to this reference position. All graphs of performance position tracking for designed control are shown figure 8. In this study, generated graphs indicate response of system for the first 5 seconds. Experimental results are obtained by considering loading condition and by comparing performance criteria. It's understood by graphs computing of performance criteria is done for 2.5 seconds, that period of reference signal. The best performance is produced by PID, CMC with PID for all conditions, and later modified CMC and CMC. We can see the result comparison for controller. Initial low load and high load. The result with PID 35, but CMC with PID 0.665. Testing steps. You can also see that the result, good result with CMC with PID with these figures. You can check our results on our paper. Okay. I want to conclude. In this study, 3 different type sliding mode controllers are designed for position control. of DC motor, DC servo system. Performance of controls are compared after implementing designed controllers to DC servo system under different load condition. And conventional CMCs is a method that produces chattering phenomenon, but modified CMC is designed by modifying switching function. It relieves greatly this problem, chattering problem. In addition, it gives better results when compared to previous control structure. In the last structure, an alternation is made sliding surface, which is a basic building block of CMC. It's understood that a controller running more stable and better performance is generated. In experimental results, although it's concluded three methods can be run on the system as a real time, it is shown that modified and CMC with PID run more stable without vibration and error. In motor control application, elimination of the vibration is so important due to the fact that it may cause deterioration and mechanical system. In sensitive running condition, as in some robotic applications, uncertainties, sudden changes, time varying loading changes, and previous position tracking, application of the CMC method provides many advantages. Okay, thank you.
Okay, thank you, Sir Akif, from Turkey. So please.
Could you explain how you obtained the results? If I understood you using Simulink, yeah?
Yes.
But you showed some stand. There is some hardware in the loop system used here, or how to relate the Simulink with the physical system?
Physical system. We use Simulink with real-time system. With Quasar, yes,
yeah,
yes.
Which
at the same time.
To the real systems, yeah?
What?
To the real signals. You have some
we used signal sinusoidal
system. Rather in the loop, you put some PCB to the computer and it converts the Simulink signals to the real signals. Yeah.
The conversion with conversion made with the Quasar. We connect the system. We get information from directly physical system directly to our computer.
It means that your controller is realized using Simulink and object is real, yeah?
Object is real.
Yeah, and controller
is also real time. We tested.
No. It contains
we design our system. We design our system in Simulink and tested on the real-time system.
Because in your picture was computer and real system, I thought that you are using it on real.
Okay. Any other question, please?
Can you go to slide number
3?
Maybe the next one then.
This is?
No, the next one then. Maybe back, I don't know. I just seen it. You passed through. Can you go back?
Back.
Yes. Can you explain what you mean on the last sentence of your statement? So this system is dedicated to something, or it is just a mock-up of made of two motors? Is it the robotic arm, or what is the purpose of this system?
In
what
this system.
You are trying to solve?
In this system, we only put like this arm. We put a load at the end of the arm, and we change the position of this arm. And After that, this is my master student's thesis. After this thesis, we made a second test with robotic arm
I understood. Thank you.
tooling.
Okay.
Okay.
I think it can be a good idea to add the experimental results or short videos about your study. It could be more effective and help you to present your experimental results. Is there any other question? So I would like to thank you because of your good presentation. I have a question before the third question, presentation. Is the Mr. Jozef Ritonja here? Okay. So at this moment, I want to invite to Mr. Algirdas Baskys from Lithuania to present his paper entitled Nonlinear Control with the Enhanced Resistance to Electromagnetic Disturbances. Yes, same is yours.
Mr. Chairman, dear colleagues, I would like to present my paper, Nonlinear Controller with the Enhanced Resistance to Electromagnetic Disturbances. I am Algirdas Baskys from Vilnius Gediminas Technical University, Lithuania. And first of all, I'd like to formulate the problem. We know that controllers that are used for the control of industrial processes often has to operate under the impact of electromagnetic disturbances. And very popular in the industry, as we saw in presentations of another authors, is PID controller. But it is electro-AMD sensitive, and the main reason for sensitivity is that it includes derivative part. And in real applications, very often this derivative part is excluded to have more higher AMD resistance. But the P controller is higher, has higher electromagnetic resistance in comparison to PID, but we know that the system response dynamics is worse when PI controller is applied. And because of this, it is relevant to develop the controller which would provide the control system dynamics similar to the PID controller, but would guarantee higher resistance to electromagnetic disturbances. And I would like to present my small idea in this field. One of possible solution, I would like to propose some modification of PI controller. And difference between conventional and this controller is that the proportional part is proportional not to error, but to error in the power, some power m. What happens in this situation? In this situation, if m is higher than 1, the proportional part, the impact of proportional part on the control system increases at high errors and decreases at low errors. It means this gives what? This improves the dynamics of control system response to set point change, to load disturbance change, and because in this situation error is high, and in the situation when error is small and control system operates close to the steady state, in this case the impact of proportional part becomes very weak, and this controller turns to integral controller, and we know that integral controller is very noise resistant. Yeah, and now I will provide you investigation results of this controller in the typical control system, as you see there. Just this, there I add the noise signal to the feedback signal, because usually in real industrial systems, very often the sensor is located far away from controller, and this line that connects the sensor with the system is affected by noise generated by various industrial electromagnetic disturbances. I analyzed this system for two different plans, one with the delay, first order with a response delay, another the third order without any delay. They are the parameters of controllers, because I compared the results of this nonlinear proposed controller with the PI controller and with PID controller. First of all, investigated the set point and low disturbance unit step response when the system is not affected by the noise signals for both these situations, and then in the table I presented the settling time, the response settling time, the settling time to set point response, and settling time to the disturbance response. If you would look to this table, you will see that this NPI controller allows us to obtain better dynamics if we would compare to PI controller, and similar dynamics if you would compare to PID controller. Now, if as the noise source was used band limited white noise source in Simulink program, but it is it looks not like a real signal. Because of this, I used some filter to make it more similar to real noise signal, and the signal was used for analysis. They are presented the unit step responses when the system is affected by noise signal with low amplitude, and we can see even at low amplitudes 003, 0025, the control system with PID controller starts operate with appropriate ripples, and the response settling time increases. If you would apply strong signal, noise signal, the view changes qualitatively. We can see that PID controller starts to operate with ripples, with control system with PID controller, and the response becomes very slow. Additionally, I analyzed the situation which is very often used in the industry when when it is used PID controller with the filter in derivative path. When I put filter to the derivative path, the response of PID controller with this filter, it was like this, and we see that the dynamics has became better, and the response is quicker, but still there are dynamics is worse than with the case when is used this proposed NPI controller, and the ripples are higher in the case of PID controller. And one more moment is we know that is very important, the robustness of the system to uncertainty of plant dynamic parameters. I analyzed the control system with the proposed controller when the parameters of plant dynamic parameters changes from minus 50 to plus 50%, and there we can see the set point step response and load disturbance step response, and we can see that the system operates stably. Of course, the duration of settling time increases, and the overshoots increase as well. And it was estimated that for the first system with the first plant, the system starts operate not stably if the dynamic parameters of the plant, in this case the time constant, increases up to 120%, and for the second plant, when both plant response delay and time constant increases by 190%, means about 3 times. In this case, system with the proposed controller operates not stably. And finally, I would like to make the conclusions. The proposed nonlinear PI controller provides the dynamics of the control systems similar to that of the PID controller. However, it guarantees a much higher electromagnetic disturbance resistance of systems as the PID controller provides. The control systems based on the PI controller operate with analyzed plans without substantial changes of the dynamic performance when the amplitude of the noise signal is less than 0.4 to 0.7. The workup systems with the PID controller at the same noise signal amplitudes changes qualitatively. The system's response becomes slow with large ripples. The low-pass filter, which is used with the derivative term of PID controller, reduces ripples of the controller parameter and speeds up the response of systems influenced by noise signal. However, the response is slower and ripples are higher as compared to systems with NPI controller. And the last one, the system with the NPI controller and plant G1S remains stable if the plant response delay and time constant increase simultaneously, not more than by 120%, and the system with the plant G2S is stable if the plant time constant rises not more than by 190%. Thank you.
Thank you for your good presentation. So, is there any question? Yes, please.
What confuses me, the controller should react to any disturbances in the system or plant, as you call, that you control. And if there are some changes in plant, I know the previous presentation was distillation column, so somebody opens the door into that chamber, any disturbance. You are trying to, on one hand, increase the proportional part sensitivity when the error is large. So that is, you are speeding up the response.
Yeah, this is
when you are getting closer, you are reducing the sensitivity. So my question is, have you tried what would happen if there is a clutter in the system itself that your system has to regulate? Not just step response, the one that you showed, but some clutter in the system.
You're talking about
to react to, and you have to regulate. For instance, you are regulating, I don't know, temperature in this room. Somebody opens the window, the temperature drops down. You have to regulate that temperature back again. So, how system would react in such a
this is exactly just a minute. The load disturbance is this, as you said, what it means, load disturbance. For example, if you have a system that regulates the temperature in the room, you open the door, suddenly temperature increases, but the system again makes that the value of parameter returns back. This is a feedback control system. It is classics, but maybe you are talking about tracking systems. I don't know.
What you are showing here, you are pushing the system into high gain region. But what would be the reaction of the system at low gain region? Because your gain is proportional to the error. And here you've made large step. If it would be a smaller step, this overshoot would be smaller. I cannot say exactly qualitatively how it look like, but this is guaranteed.
That would result in reduced gain of proportional part, and this means that reaction will be slower.
Maybe. But I analyzed more difficult situation.
Okay, please.
May I ask about the control itself? Could you show
the formula?
Yeah, the formula. You have a signal, which means that depending on the error, whether it is positive or negative, you have a positive or negative gain, which means it's a positive or negative feedback. Negative in general. Why you introduce?
Now, if you would go to the classical PI controller, you would have proportional coefficient multiplied by error. Yeah. But there you take absolute value. Yeah, because you put into the power, you cannot. This is just this term is just gives information about error signal, error sign. Because in classical PI controller, you have negative and positive errors. Yes, if error would be negative, would be one situation, and an I would be another situation. But if you would do like this all the time, this term would be positive. It is not good, because at negative error it should be negative. Yeah, this is just sign. Yeah.
In general, yeah, the control structure is stable in classical PID control. Yeah? We have a negative feedback, and the gain and the positive gain is constant. And okay, the signal is negative or positive depending the.
If the output is higher or lower in comparison to set point, yeah. It is. It should.
So we
No, it is like this, yeah, because you know that proportional term would be positive if the set point would be higher as output, and an opposite would be negative, and it should increase or decrease the parameter. It works, and it is not error. Yeah.
It works, but I just wonder why to write signal here.
Because there is a modulus function in the error. So they have
Yeah. I never would have negative term.
yes. So
But this n, what values?
Values m more than 1. If you see to this, there was the table.
Maybe the square. Maybe
Just a minute.
But it can be 1 by wave shape. There was in your table before.
Yeah. Oh, well, there is a parameters. If you mean this m is for this 3, for this 1.84.
is there any other question? So but very short question.
Yeah.
Are there any problems to achieve this system with your controller with anti-vanguard?
It can be, of course, it can be added, yeah.
So I would thank you because of very good organized slides. I really thank you because of that. The thing that I really satisfied me was the organization of the axle in the figures. For example, in slide 5, 6, you can find everything is starting from 0 to specified number, also about the vertical and horizontal axles. So it was very good organized, and you were very fluent. Thank you for your presentation.
Thank you.
I would like to
Thank you.
invite to Mr. Pawel Dworak to present his next presentation entitled Environment Mapping Algorithm using Semantic Description and Constrained Delaunay Triangulation. Okay, please.
It's again me. Right now I'm presenting results of work of my colleague Daniel Figurowski. So it's mainly his work, and it's about environment mapping by a, in general, robot. But I presented the research problem and some current solutions and some current proposals taken from the literature. I present the main our motivation, his motivation to the work, the proposed method and simulation results. In general, the problem is how to control, for instance, a robot, and in much natural way. It could be better if we could ask a robot to find a cup of coffee or something like that. It's much more natural for human being. In fact, right now we have to do some precise coordinates to the robot where it has to go. So the problem is easy to formulate, but it's much more difficult to solve. That's why we have a lot of works on such a problem, like here, the maybe not the newest, but many researchers are trying to construct such a system which use semantic maps, with the help of semantic systems, which aid the robot, aid human beings which operate robots to find a better paths, robot paths. Or for instance, if a robot is trying to search let's say a building which is not well known, in order to find some specific space like a kitchen in here. This robot has to find itself in the building and to build the map of the building, topological, and in our case also a semantic map of the building. So they are trying, many authors are trying to construct such graphs, different categories for the different objects, and as the robot is going is searching through some spaces along of the topological map, he creates also, he adds some specific semantic elements, and maybe I skipped these details. We don't have enough time for that. In general, the robot has to do two tasks simultaneously. It has to localize itself and build a map. And even in such a simple system like here in our corridors, even if the robot is going through these corridors, like from point A, C to B, if he takes the full circle, his map may be quite difficult from the original one. Yeah? So there is a lot of tasks, both topological and also semantic. Yeah.
Yes.
Our research motivation is to develop the control methods which use adaptive semantic models to increase the efficiency of the mobile robots and some exploration process. So it's a general task, but today we are talking about some small issue which allows us to create such active SLAM, which for specific criteria we can plan, explore, plan the road of the robot better and control the robot better to do much more efficient measurements and to build them up quicker. So a part of this typical task, which is exploration and planning, we have also a task. It is the task perception, a semantic task. We don't say that the robot is going has to go to some specific point, but we say that it has to go to, as I said before, to the kitchen. Yeah. So we create also some topological and some semantic map of the environment. And in the paper environment mapping algorithm, we are developed some algorithm which allows us to build a semantic map of the environment. And if it's our environment, we have some specific regions different from the point of semantic There may be a kitchen, there may be a living room or something like that. There is a path along which the controller is going to, let's say it's going to go, and depending on which point, we have to build a map. Yeah, it's an area which is going to be visible by the robot, and our task is to build a graph, build a map of the environment of this white area, but also describe it as precise as it's possible, and to build some relations and to build some borders between between different semantic parts of this environment. We are using a Delaunay triangulation, which is a triangulation. So the area the robot sees is separated is constructed from triangles. There are some specific triangles. It's a Delaunay. It's triangulation. It's not. I'll show what is the difference, because in Delaunay is algorithm is also connected with Voronoi diagram, for which each circle which goes through these three vertices, construct the middle of this circle. We construct such a we can construct another controller, and we minimize the angles of these triangles. Like here you see we have to avoid such edges and construct triangles like that. It allows us to minimize the number of these triangles in the whole net, and it allows us to use that's such a method of writing the environment, and to use another search methods, which is the nearest neighbor search method, because these points, this middle of these circles, will show us where is the nearest neighbor of the point where we of consideration. Yeah? The algorithm is there is a Delaunay triangulation with constraints, because in case of such situations, such areas like here, we have to avoid taking into consideration these areas, and such a map, as I presented before, constructed by a robot. It was a simulation only, and it was the robot was analyzing the environment, the area around it, in some specific point mentioned here, specific here, and is able to construct the precise map of the known environment, and can construct also borders between these semantic areas. And of course, if he acquires the knowledge about some new area, he has to decide. The algorithm has to decide whether it's semantic compatible with the known word. For the it has to decide whether there is a proper spatial relation, so the area is a part of another area inside the known world. Of course, we have to data match and data reduce the number, for instance, of these triangles in the net. So okay, here we have to specify conditions how to construct the known world with a piece of new world to create another let's say set. And just to verify the algorithm, there was a simulation of its environment for the robot. We have a terrace, garden, corridor, living room, and the virtual robot path, which consists of 24 points, and we are checking how the algorithm works if we increase the number of data, amount of data which has to be calculated, and so we increased. We virtually moved the robot around this circle many times. So we have a lot of virtual points which are a bit shifted, because it's unnatural that due to some disturbances, the same area visible by a robot seems to be a bit different from the previous measurements. So we have a lot of thousands of points, and the algorithm has to recalculate that to create a proper borders of and the map of an environment and the proper borders between these semantic segments. And we see that even if we increase the number of loops and iterations, the number of measurements, the loops iterations mean time is increasing, of course, but it's not it's acceptable. The number of triangles is still minimized, and also up to some specific number of iterations, we still do it quickly, and so we can do it quickly, and we can improve the precise knowledge, and we can limit, for instance, of the border, the distance of the border. We can be more and more accurate. So it depends on us what to use, whether we would like to precise know the environment, or to recalculate and to build the model very quick, and maybe not as much accurate. But it is possible, it works, so it's a first, maybe not first, second or third step in our general plan to construct the whole algorithm. Thank you for your attention.
Okay, thank you for the presentation. Do we have any question?
Did you make any real-time experiments with your methods?
No, it wasn't real time. It was simulation. But in general, the times are where all simulations were done on the same computer. So it's so we can. They give a broad idea how long the algorithm would work in a real-time platform.
Which simulation are you using?
What?
Which simulation are you using?
Simulator.
It was mainly done in MATLAB, plus some additional elements which model the environment.
If you apply this method to real-time system, which time sensor, which kind of sensor are you think? Which kind?
Here we have we don't consider the problem of semantic, analyze of all objects we see. Yeah, but of course we have some devices which measure the distance just to build the environment, the topological environment map, and it may be also a camera, but it hasn't been used yet because of the early stage of the research. Yeah?
Maybe you can try the camera data with your simulation. Obtain for example.
Yeah, it's obvious.
Kitchen,
Yeah.
In the kitchen, fork, spoon, and dish.
Okay. In general, in the system, as we see that, the problem of checking what type of environment it is and what we see, we can do by using some prepared by other scientists, for instance, nets, and we can use, for instance, a deep learning, but the neural networks which recognize different objects, and we can simply use that in our algorithm, but just to analyze the environment.
So the largest dimension that you tested by the simulated environment. The distances can change the condition of the control.
The simulation was done with the use of the package, in which additional package in which we could model and create let's say a virtual world. And so the distances were not huge. Yeah? It were just for checking the algorithm.
So we can investigate it. Yeah.
Yeah.
Okay. Thank you for your good presentation.
Thank you.
Thank you. For the last presentation, I would like to invite to Mr. Jozef Ritonja from Slovenia to present his presentation titled "The Control of Batch Bioreactors."
Chairman, gentlemen, Chairman, how much time do I have? How much time?
You have totally 18 minutes.
18. Okay, this is
with
good.
questions.
This is good. Okay, because we are right. So, I'm Jozef Ritonja. I'm coming from Maribor, from Slovenia, from University of Maribor, and I will present the paper with this title. There are three authors, me, from Faculty of Electrical Engineering, and two ladies, Professor Andrea Goršek and Professor Darja Pečar from Faculty of Chemistry. The topic of the paper is how to control a batch bioreactor. So, and if you would like to develop control system, it is necessary to know the mathematical model of batch bioreactor. So this is the subtopic of this paper, modeling of batch bioreactor. This is first question: are bioreactors important? So bioreactors are good things. Remember yesterday, thanks to bioreactor, it was so nice evening. Bioreactors is produced beer. So, but is control of bioreactor also so important that it is worth to write a paper for conference? Answer is very short. Yes, they are really very important. There are two reasons: food and drugs. So for 8 million people, we need really a lot of food and drugs. And to produce this, we use biotechnology, and this is one of the most rapid growth industry in the world, and the heart of all biotechnological systems are bioreactors. So I will shorten a little bit my presentation. First I will say some words about bioreactors. After then I will develop the mathematical model for bioreactor, describe the proposed control system, show experimental results, and some conclusion remarks. So, what's bioreactor? Bioreactor is a tank. It's a very simple thing. It's a tank or a vessel where the biological process is carried out. So inside the bioreactor we have three. We have many things, but three are most important: cellular biomass, these are cells or enzymes, substrate, and desired product. What happens in bioreactor? So there happens many different biological processes, but the most important biological process which is carried out in bioreactor is fermentation process. In this case, we have cellular biomass. These are cells or enzymes which converts the substrate into the desired product. We have always these three things. So in yesterday's case, we have yeast. This was biomass, which converts starch to the alcohol in the brewery. Is it necessary to control fermentation process? Fermentation process is quite simple process. It will never be unstable, because when the biomass will eat all substrate, the stable will finish. Yes, it is necessary to control the fermentation process if you would like to obtain high quality desired product, and if you would like to shorten the production time and to make the production more effective, more cheap. There are many different types of bioreactors. This is the universal scheme. We can see this is a tank in the middle. Tank is it here? Yes, tank is isolated, thermal isolated. We can put substrate and biomass during these pipes, input pipes with valves and feeding pumps. After then, when the process will be finished, we can pump the results, our desired product, during these pumps and these pipes. We have a lot of sensors inside. We have heating system to have the constant temperature, and we have also steering system, so to which rotate and homogenize the medium inside the bioreactor. There are many types of bioreactors, but three are the most important: continuous, fed batch, and batch bioreactors. Continuous, what is the difference? By continuous bioreactor, we can change input medium and output medium during the operation, during the fermentation process. We can increase or decrease the inlet of the inputs, and we can also make the same for the output. So, what is happening in fed batch bioreactors? In this case, we can change during the operation the amount of input mediums, but it is not possible to change during the operation the outlet from the reactor. So when the fermentation process will be finished, we can open it and pump the desired product from the bioreactor, but not between the operation. So this changing of input mediums could be made continuously or in some time discretely. The most simple are batch bioreactors. In this case, we cannot do anything with the input and output during the operation. We just open the reactor, put inside all the things, close it, and fermentation process starts, and we wait. 1 day, 1 week, 1 month. So this is the most simple bioreactor. This is the advantage of batch bioreactor: price, simple maintenance and operation. And disadvantage of this bioreactor is that there is no input variable to control the fermentation process. And the idea of the paper was, is it possible to control the fermentation process in batch bioreactor by changing of temperature of the bioreactor? So it is quite new approach that there is not used in the models which are sold on the market. About mathematical models, there are many mathematical models, but the models in chemistry are a little bit other than our models in electrical engineering, mechanical. So where all models are written in form of state space, nonlinear or linear mathematical models. In this case, there are models which are based on process kinetics, and the classical, the most conventional mathematical model is a model which is based on the mass balances of these three mediums: biomass, substrates, and products. And model is quite simple: three differential equation. X is cellular biomass, S is substrate, and P is product. You can see here there are three first order nonlinear, very nonlinear differential equation. We have two parameters, alpha, beta, and what is the most important is the function mi, which is specific growth rate, and this is the most important function, the most difficult to obtain it. So there are many descriptions of this function. We can see mi depends on substrate, of concentration of substrate and product. So this is better approach, and this is more simple monodose function. So this is the most conventional model of bioreactor. This is model which is used for all three types of bioreactors, but in this case it is not used for us because it does not describe the impact of inputs, in our case temperature, on the fermentation process. Therefore we have to expand the mathematical model. We did it experimentally. So this is one, we use this bioreactor. It's very small. It is laboratory bioreactor equipped with a lot of sensors and all these things to determine thermal characteristics. And we use this bioreactor, and the fermentation process, which was be analyzed, was the process of the production of kefir from milk by means of kefir grains. This was very oftenly used process. It is very difficult to measure output product. Output product is in this case kefir, the concentration of kefir. It is much more simple to measure the carbon dioxide, CO2, and there are direct connection between the concentration of the output and the concentration of concentration of the kefir and CO2. Therefore, we use CO2 for controlled variable. Here in this figure, we can see the response, what happened in the bioreactors. So this is obtained, we have constant temperature, we have constant steering rotations. And what is interesting with this figure, first, time axis. The entire process will be finished in 100,000 seconds, so in 1 month. So, and second is, it is also very interesting that it is, the time response is very similar to the response of the step response of the first order lag. Yes, it must be because it is also written in, if we calculate with the monodose model, we will do the same time response. So what are the consequences of the changing of the temperature on the bioreactor, on the fermentation process? So we can see this in this figure. So the blue one dashed line, this one is the same as before. This is the response, time response of bioreactor with constant temperature 22 degrees. And this black one, solid line, show if we change in this time, it is 10,800 seconds. If it change the temperature of the medium in the bioreactor, the production will be such way. So we have increased production. We made a lot of different tests. It was quite a lot of work because we need a lot of time, and we test it also on many bioreactors. We change the temperature at the beginning phase, in the middle, or in the end. We make larger or bigger increases in the step changes, up or down. So, but in all cases, and based on observation of these experiments, we found the solution, the proposal that we could describe the mathematical model for this bioreactor, which will include the influence of the temperature on the bioprocess. We can model we can describe such mathematical model by 2 parts. Are you sure? You are not.
I'm not sure, but I want
but
to.
Yes. I know how much is time. Yes, therefore I ask you at the beginning. It is 20 minutes. I have 6 minutes together. Okay, I will increase the speed, but therefore I ask you at the beginning. Yeah. So in other case I will be shorten something. Yes. Okay, the mathematical model which we suggest for such process is shown on this figure. This is here bottom is the autonomous mathematical model. This is the same as proposed before, and this is the supplementary input-output mathematical model, which will describe what happens if temperature in bioreactor will change, what will happen to the production of the bioreactor's output product. So, and we after the estimation observation, we can say that it is possible to describe this supplementary input-output model with very simple parallel connections of first-order lag and, here bottom, second-order lag with differentiator part. The first-order lag denotes the major dominant connection between temperature and the dynamics of CO2 release, and the second part is important in transient response during the transient. So we identify the model. We use least square identification method. And we obtain these results for first order lag and second order lag with time with differential. Here are the results of the simulations of the obtained mathematical model. This is the black line and the measured difference, so of the obtained from the measurement. So control system is very simple. It is based on three parts: measurement system, the generator for reference trajectory of output product, and the controller. Because the control process was not complicated, two parallel first order and second order lags. There is very simple thing to control. We use simple PI controller. We use basic school tuning procedure. First we determine time constant. After then we use root locus diagram to determine the gain of PI controller. We obtain these values. This is the procedure how we calculate the gain by using root locus diagram, and here will be the results. This is the reference trajectory of the desired output product. This trajectory is proposed by technicians from the industry. They have a lot of experiences. What kind of the reference must be to obtain good high quality output, and here are experimental results. You can see the blue one dashed line. This is the reference value, and the black one is very close. There is the real value of the output variable. It was not too much to do. This is how much we have to change temperature. Not plus minus 10 degrees. We just need additional cooling system. It was not only to heating, but we need cooling system at the beginning. But there is nothing. It is the dynamics is not critical. Also the values are not critical. Conclusions, very fast, 10 seconds. First, we show that the growth of microorganism could be controlled by heating system. So by this heating system, we can assure that the output of the bioreactors will be very close to reference trajectory, and the consequences, the fermentation process will be of high quality. This will skip, and yes, the operation of batch bioreactor is significantly improved by means of this procedure. What will happen in future, we will see. So, okay, thank you for your attention.
Thank you for the presentation. So, is there any question? Please.
Did you analyze the disturbance response of system?
There are not conventional. There are uncertainties in the system. There are the problem because it happens something in the bioreactor, but there are not conventional classical disturbances from outside. There is always, it is closed. It is nobody opened the window or something. Yes. So this is the main problem is to follow. This is not regulated. Yes. This is not the regulation problem. This is the tracking system. Exactly as you told me. Yes.
Thank you.
Okay. Any other question?
How long does the whole process take?
Fermentation process.
Yeah, the fermentation.
Yes, this one was 1 month.
10,000 seconds.
Yes,
yeah.
1 month.
But okay, but what is the condition for stopping?
That all the fermentation process is finished when there is no more food inside the bioreactor. If the cells eat all substrate.
Okay.
So, but we can increase the speed. So this was our goal. So instead of
okay, that's
yes.
why I'm asking, because of the next.
You can see here.
result.
There are about
Okay,
figures
yes.
here. Yes, you can
Because
see.
if there is no food, there is no CO2, and if we see that the concentration of the CO2, if we increase the temperature, there is more CO2.
Yes.
So it means the process is not finished.
No, but it will finish. It will increase in
The amount
transient.
of CO2 should be the same, no matter whether it's in lower or higher temperature.
No, because the biological process depends on the temperature. So you have better or less or worse efficiency of the conversion of the substrate to the desired product. So you can during the operation, what happens? So without changing of temperature, the concentration of cells increase, the concentration of product increase, and the concentration, so exponential, very simple, yes, and the concentration of substrate decrease, also exponential. So, but if we change the temperature, in this case, there will not decrease the concentration of cells so much, it will increase the concentration of output product. You know, it is quite strange for us. I understand you that you are confused, but it was also for me very surprisingly.
Okay, about the temperature, which is the limitation of the normal limitation of the temperature for a bioreactor?
It depends on type of bioreactors, and it depends of the mediums inside. Yes.
Simulation and experimental results from 22 till 27.
Yes. This was.
So what is the reason of this limitation?
It depends on type of bioreactor, and it depends of the fermentation process inside. Mm-hmm. It is similar like by electrical machine. We can destroy the machine, the permanent magnet, if we have too high current. It is similar here. If we have too high temperature, some cells will be killed. On another, so perhaps for milk fermentation, it is more sensitive to changing the temperature. In case of alcohol fermentation, starch fermentation, there are different. But in this case, there are no problem. I think I can say so by hand, plus minus 15 degrees. There is allowed in every case.
Yes. Okay. And only the temperature is the parameter that can affect the system, or is there any other parameter?
Yes, exactly. I was shortened. The other is the steering, the rotation speed of steering system.
Yeah.
We have steering system inside, so we can do two things with bioreactor. One thing is to give the heat in the bioreactor. This is to change the temperature, and the second thing is to give the mechanical work into the bioreactor.
Okay.
Power, this is mechanical power, and this is steering system. Yes, exactly. Okay. We can do, but it is more simple to change temperature. So this is the reason that it's used for practical realization.
Okay. As a suggestion, I think if you add some experimental results, more experimental results, or your prototype, it could be a good idea to more explain about your prototype, especially to our
Thank you.
researchers.
Thank you for your suggestion.
Thank you for your presentation. Thank you for your attention in our session. So I close this session and invite you to the coffee break. Thank you.
Thank you to everyone.